Hi, class. Today we look at another in the lecture series that is before us to accomplish before the semester ends. The topic that we're looking at today goes by several names. So depending on where you are looking, you will see the topic as the theory of mass service. You may see it as congestion theory. You may see it as traffic theory. You may see it as stochastic service systems or queuing theory or even waiting line models, right? So we know that a queue is synonymous for a line. And we know that queues are part of everyday life. We all wait in queues, whether it is to make a bank deposit, whether it be in the bank or at the ATM, to pay for groceries, to obtain food in cafeteria or Juicy or BK, wherever we buy our lunch, or to ride on the plane. We have become adjusted to waiting, but of course we still get annoyed, if we have to wait for unusually long times. The queue models then are very helpful for determining how to operate a line, a queue system, in the most effective way, especially if too much service capacity to operate the system involves excessive costs. The models, and there are many models of queuing, enable us to find an appropriate balance between the cost of service and the amount of waiting that the customer will have to do. So basically, we're trying to figure out who should pay the cost of waiting. Should the company bears the cost of improving the service quality so that the customer doesn't have to wait? Or should the customer, well, just wait with minimum service capacity? Now, we wish to go through the topic according to the headings outlined, and at the end of the lecture, you should be able to do these following learning objectives, 3 of them. The third one will just be a little introductory question, no deep analysis, but at least you should be able to do a simple analysis of a waiting line, cost analysis to be specific of waiting line. So queue theory, as I indicated, is the study about waiting in lines. And we know that waiting in lines are common, they're a common part of our existence, right? But they're not just for our everyday life. You find that in the manufacturing, especially and service sector, that they are very useful in helping to manage the waiting process. Now, this table shows common queuing or lining up situations. When you look at them, at one point, any of us who is listening to this lecture would have been in one of the situations here listed. And there are multiple other situations that are not listed. So for example, quite a number of you will be taking the plane to go to your summer job abroad. That's a queuing situation, whether it is to get through custom, to get on the plane, to find your seat, to get off the plane, to go through custom, to exit the airport. That is really one long queue process. So all of us at some point have been in official queues, unofficial queues. It is a part of our existence. So when you look at the common queue situations, you have them displayed on the screen. At some point we have been in one of these. So it is inescapable. It is an inescapable part of our existence. Now, when we're looking at queues, we tend to look at them, but not 10. We look at them within 3 headings, the characteristics. We call them the characteristics of waiting line systems. We look at our arrivals, our inputs to the system, and we look at that under the heading of the size of the population, the behavior of the arrivals to the queue, and the statistical distribution of the arrivals to the queue. On the queue discipline or the waiting line itself, we look at the length of the line, we look at the discipline of people or the items in it. So when we talk about people, you have to consider that loosely because people here is really in quotations, right? So people can be machines. So you look at people in quotations. Machines, cars, anything. So people is used loosely. And then we look at the service facility itself, the design of it, and the statistical distribution of the service time. Good. So here is a pictorial of the parts of a waiting line, right? So here you have the arrival characteristics. So here, here you have the arrivals to the system. And the arrival characteristics, under the arrival characteristics, we look at the size of the arrival population. Well, what exactly about the size do we look at and how do we think about the size? Well, we think about the size as being finite or infinite. Finite mean limited to specific persons or things, or infinite. It is not, what's the word I'm looking for? It is not, I don't want to use the word limited, but it's not constrained to a particular set. So for example, limited would be, or finite would be, only persons who are sitting exams can go into the exam room at UTech for a final exam, right? So that's limited or finite. Infinite would be anybody can walk off and sit down in a lecture, right? It's a public institution, so anybody can really come and sit in the lecture, not in the tutorial. So when we're looking at arrivals to the system, we first talk about the size of the arrival population. So if you look at this, Dave's car wash, you see that the population of dirty cars here, population of dirty cars, in the great scheme of things, it does not say what kind of dirty cars should come to Dave's car wash. Any dirty car can walk or drive off the road and come to the car wash. So in that sense, we will say that the arrival population is infinite, right? The behaviors of the arrival, when we talk about the behaviors of the arrival, we're talking about when you come, what do you do? So the behavior, we talk about the behavior in terms of the patience, one of the arrival. So we say that you're a patient arrivee. And when we talk about patience, we mean that you wait in the queue, and if there's more than one queue, you do not switch lines. You simply wait in yours and go up. And so we also say that there is no balking. I'm writing on the board, or reneging. Balking simply means that if you come to the queue and it's long, you say, yo, whoa, it's long, and you turn away. No, that's balking. You don't do that. You come, no matter how long the line is, and you join the line. Reneging simply means that you do not join the line, spend a few minutes going, and then it's too long and you leave. And neither is there no jockeying. Have you ever seen horses racing at Caymanas Park? Maybe not in person, but on the TV. And they're always trying to bore through each other to get to the front. Jamaicans love a skip in the line, right? So no skipping the line. That is what we call jockeying. So your behavior is that you're patient, you do not balk, you do not renege, and there is no jockeying. So that is what we mean when we talk about the behavior of the arrivals. Now, the arrival pattern is thought to assume a particular statistical distribution, and that statistical distribution is something you would have encountered in statistics called the Poisson distribution, right? Now, what about so there is the arriving population. So what about when you have actually joined the line? So that's in the queue, in the line. Now, we describe the line as either being finite also. So, well, let me say this. A queue, that's a line, is usually characterized by the maximum permissible number of units that it contains. So we also can say the queue is finite, that is limited, or infinite, that is unlimited, depending on the number of persons that are allowed in there. Now, the queue discipline is how the persons, remember I said persons are used loosely, how the persons are dealt with in the queue. So the queue discipline is usually assumed to be first in, first out. That's the most common. But you have other priority rules that may be used in special circumstances. So when you're lining up to go on the plane, it is not who comes first to the door of the plane, it's the first class passengers, then however they board them, right? According to the class of the tickets that you have. If you go to the hospital and you're sitting down there waiting on the doctor, even though you would have been there from 2 o'clock in the morning and it's now 10 o'clock and you're just get your turn to go into the doctor, if the ambulance screams and comes in, then the doctors are going to run and leave you and go and tend to that emergency patient. So in the hospital, you expect that the way to deal with the people who come to the hospital or line up to use the hospital services, emergency cases first, right? So it is not always a first in, first out that defines the queue discipline. It could be other rules, but we usually assume that it is first in, first out. Right now, the service characteristics. So let me give that another color. The service characteristics. We look at, here in the service characteristic, we talk about the queue system designs, whether it's a single server, multiple server, single phase, multi-phase, meaning that, so here you have just one service area, so that is what we call a single server, single phase. So you just come in, you wash, and you exit the system, right? So the service characteristics looks at the design of the service in terms of how many servers are there and how many phases there are to the service system. And in a minute, I will show you a number of service design systems. Now, the statistical distribution of the service entity is usually assumed to be exponential. So we have Poisson arrivals and exponential service systems. Now, remember that, or you may not remember from your statistics, that Poisson, the Poisson statistical distribution and the exponential distribution can be made to look like each other depending on some assumptions in there, right? So they're not disparate from each other. So keep that in mind. So again, I have to erase my board. So give me a second, please. All right, so these here just talk about the arrival characteristics. So just to reiterate, that when we're talking about the size of the arrival population, we're looking at whether it is finite or infinite. When we talk about the patterns of arrival, we're talking about how did you choose to arrive at the destination? Did you come randomly? That is, you just get up and come on your own, or was it a scheduled appointment? And your arrival often patterns the Poisson statistical distribution. How do you behave when you arrive to the line? You are patient. That is, you do not switch lines if there are multiple lines, and you wait your turn for however long you need to wait in the queue. Also, there is no, let me write jockeying. You do not balk, meaning you do not come and turn away if the line is too long. Neither do you renege. That is, you do not join the line and wait for a few and then leave it. And neither do you jockey. That is, you don't go and beg your friend that's skipping the line, right? So just to reiterate the things we talked about on the previous page. Also, the line itself, remember I said that the line itself, that is after you come from somewhere out there, come and join the line, the length of the queue can be regarded as finite or infinite or limited or unlimited. And the discipline, that is how it is that you call the persons or the things from the queue for service, is most oftentimes done on a FIFO, that is first in, first out basis. But remember, for example, if you're in the hospital, that other priority rules may be used. If I talked about if you're going to board a plane to go away for your summer job, that it is not who arrives at the plane door first. It is those people who have first class tickets that will be called to come in first or to queue up to come into the plane. And if you're in the hospital, another example, it is no matter how long you have been there, it is emergency clients who are dealt with first. Good. Now, the service characteristics, meaning that we're looking at the queuing system design, meaning what do the line look like, or what do the lines look like? So we say you have a single server. It can be just a single server, I mean just one piece of equipment, one person dispensing service. So when you go to the ATM at VMBS on campus, it's a single ATM, single server that is dispensing the service. There can be places like when you go to BNS out in Papine or at UWI, you have multiple ATMs, that's multiple server. When we talk about the phase of the system, we're talking about the different parts, the different things you must do to get service completed. So when you go to the ATM, you simply go in and you come back out. So that's a single phase. When you go into the banks, you have to go to security, take a ticket, go and sit in line, get something vetted, get some information. Then you go to the customer service, and then the customer service may take you to the teller, and then you get your service. That is multi-phase, meaning you have to go through multiple phases before you get where you're going. Or when you go to the airport, that's a good example of a multi-phase, right? You have to go through several entry points or checkpoints before you're able to exit the airport, right? Now, just like how the arrivals have a statistical distribution, which we call the Poisson distribution, the service time also has a statistical distribution, which we call the exponential, negative exponential. It's written like this, that big E, negative E to the negative X, right? And that's we call the negative exponential distribution. We just usually say exponential distribution and know that that is what we're talking about. Now remember that I said that the Poisson distribution and the exponential distribution are not mutually exclusive. They can be made to look like each other depending on the assumption that is made about the exponential distribution, right? So here is a pictorial of some Q system designs. So for example, when you go to your family dentist, I'm not talking about the big practices where you have multiple people and you get to go to whoever is available. Talking about your little family dentist, the one that your parents, usually your mother, takes you to from you were a little baby until you choose not to. So here you arrive, you queue up, meaning you don't necessarily stand up and form a line, but you know you go in and ask who's next, etc., etc. You don't have an appointment, and so you form the line that way, and then you go see the dentist. So here's the dentist, and you depart, right? So in your little family dentist, it might just be himself or herself who does everything. Well, these days everybody has somebody to help them at the front office, but I'm simply talking about the service facility, right? Good. So if you go to, well, it's more Burger King. We don't have McDonald's out in Kingston anymore. So a Burger King dual window drive-through, right? So you arrive, you enter the queue. The phase one, you can, after you order, you go up and you pay, right? After you pay, you go on to picking up your food, and then you exit out onto Barbican Road, or you go into the parking lot and go about your business. So that's a single server multi-phase. So notice that at each phase here, it's one person who takes the payment for the order, and usually one person who gives you the food at the window. So when we talk about queue designs and phases, those are the ideas you should have in your mind, right? Pressing my board again so that I can turn the page. So here you have most banks and post office windows. You have a single that we call a snake line. That one long line that snakes around. So you have a long snake line, and you have multiple server channels, multiple tellers or people who you can go to. Anybody has ever been to Ligonier Post Office? I know post office are not popular anymore. But at least if you've never been to the post office, go into Ligonier Post Mall and walk into the post office. That's how the post office is set up. You usually have one long line for posting, etc. And whosoever is free, you go up to them. But we have all been to the bank, and you know you have one long line, and whichever teller buzzes that they're free, you go up to that teller, right? And so we have experienced almost all of these queue systems at some point in our existence, right? So these are some pictorial of queue system designs. And we have, well, when you go to Juicy, this more looks like what you will encounter when you go to Juicy. Multiple server, multiple phases. You queue whichever side of the queue you go to, whether it's the patty side or the cook lunch side. You queue up and you get your lunch. So here is maybe the patty side. Down here is probably the cook food side. and you get your lunch, and then now you go to the cashiers and you're free to join whichever one, and then you go out into the cafeteria to sit and have your lunch, or you exit Juicy completely. So they have this type of design in the Juicy cafeteria, and it's called a multiple server, multiple phase. So there again, that I said that we have pretty much experienced most, if not all, of the different kinds of queue system. Yeah, we just never usually pay attention to what they were, right? No, we measure the performance of the queue in order to help us to decide how to balance the cost of providing the service with the cost of waiting. No, waiting does have a cost, whether it is in time you miss at work, time you miss your class, or time you could have spent using to do something else, doing a question before you come to decision science class. So when you choose to wait in the line, and it's a choice, you don't have to. Remember, from decision analysis, do nothing is also an option. You could have just leave the food and, gone about your business. So when you choose to wait, the time that you use to wait has an opportunity cost. So we want to balance. We assess the line so we can balance the cost that the customer will incur in waiting and the cost of providing maybe a quicker service. So what is it that we look for? What is it that we measure in measuring the performance of the queue? Well, we tend to measure 7 things. We tend to measure the average time that each customer, and remember I said the customer is or the person or object, right? So we use person quotation. So we measure the average time the person or object spends in the queue. We measure the average queue length. And remember, the average queue length can also be called the number of persons in the queue. So the average queue length can also be called the number of persons in the queue. We measure the average time each customer spends in the system as a whole. So what do we call average time in the system, right? So it's the time that elapses from the commencement of the service to its completion for a unit at the service facility. That is known as the time in the system, right? So it's the from you enter to the time that you leave. That is what we call time in the system. We also measure the average number of customers in the system. We also look at the probability that the service facility will be idle or the service provider is idle. We also look at the utilization of the utilization factor of the system. Usually that is the probability that the system is being used or that the service provider or the service facility is busy, okay? And we also look at the probability of a specific number of customers being in the system. But when we talk about queue performance or queue characteristics, we usually are referring to the first 6. The 7th one, you should wait until you're asked specifically about number of customers in the system. Right? So usually when we ask you a question such as measure the characteristics of the queue. We expect the first 6, and you wait until we ask you about the 7th one for you to do something about that, okay? So here is just a pictorial of the trade-off of the queuing costs. And it's really a simple diagram. We notice that here is your service level. And we notice that the orange line, the cost of providing service, it increases as the service level improves, meaning that as the number of service entity improves or increases, that the cost of providing the service will increase. On the other side, however, you have the cost of waiting. So notice that as the number of service entity or as the service level increases, that the cost of waiting declines. So it is always the opposite for the both parties. To improve the service, the cost is going to rise for the provider, but the improved service is going to cause the person using the service to have a lesser cost in terms of waiting time. So the equilibrium occurs at a point left of where you have the minimum on the total cost line. So notice that there is a gap between the cost of waiting and the cost of providing service, where at the minimum cost, the minimum total cost, you have the cost of service being higher than the cost of waiting. So you find that companies are trying to move the equilibrium down to the left from this occurrence at the right-hand side. So we're looking at how to balance that inequality in the costs, the two costs, right? All right. There are 4 queuing models that we can do. We're just going to look at them quickly, right? But the models assume that the arrival to the system follows the Poisson distribution, and that the queue discipline, that is how we call for service from the system, is a first in, first out system, and that it's a single service phase, right? Now, we're going to confine ourselves to just one of the phases. Now, when the phases become multiplied, well, the mathematics also becomes multiplied. All right, so we are going to be looking at the simplest model. And that is the model that is called the MM1. It gets its name from a notation that we call Kendall and Lee. Those are the persons who came up with the notation. The M really stands for Markov. And you would have recognized that from statistics. So the MM1. The MM1 here simply means that the Number of service channels is single. The number of phase is single. So the M now talks about your arrival pattern. It's the first M, which is Poisson. The second M talks about your service time pattern, which is a negative exponential. And the 1 talks about the number of service provider. So MM1, M stands for Markov. Remember I said, so you're going to think, so how M is standing for Poisson and for the negative exponential? Remember I said earlier that they are not unrelated, that the exponential can be made to look like the Poisson depending on the assumption you make about the exponential, right? So the MM1 simply talks about the arrival rate, your service pattern, and the 1 talks about the number of servers, right? And that characterization comes from what we call the Kendall and Lee notation, right? Always have to take a little time to erase the board before I move on. So there are other kinds of queue models or queuing models. There is one where you call the multi-server MMS, where you have, though you have single phase, you have population size is unlimited. So like your airline ticket counter, MMS, you have the constant service model, the MD1, and you have the finite population with finite source. But we are going to be looking, as I said, at the simplest kind of queue, which is our MM1, meaning Poisson arrival, exponential service time with a single server. Now, to describe the single server, single line, single server model. Again, just for emphasis, the arrivals are served on a first in, first out basis. Every arrival waits to be served regardless of the length of the queue. Arrivals are independent of preceding arrivals. That is, and the average number of arrivals does not change over time. Arrivals are described by a Poisson probability distribution and come from an infinite population. Now, while service times may vary from one customer to the next, the service times are independent of each other, but we know the average rate of the service time. So not everybody is going to take the same service time, but on an average, we know what the service rate is. Note that service times occur according to the negative exponential distribution. Now, point 6 is very, very important for when you are going to work the problem. So I'm pointing that out. Point 6 is very important for when you're going to actually work out a problem, that the service rate is faster than the arrival rate. The service rate is known as mu. That's the average service rate, mu. And the arrival rate is known as lambda. So mu is always greater than lambda, or you can write it the other way. Lambda is always less than mu. So when you get a problem to work, if mu is not greater than lambda, or if lambda is presented as being less than mu, it means that must be rectified by you, the worker of the problem, before you can attack the questions. If you do not get that right, then it's just gibberish that's going to result from your working. In your tutorials, you will get practice on how to make your mu and your lambda fit this sixth characteristic here. Always tend to that first before you begin to work the problem. Of course, you must read the problem to see that it is so, right? Good. So remember that for working the problem, point 6 is of the utmost importance in terms of the working out of a problem, right? Now, so we continue. We're going to look at the formulas that we will use to determine the characteristics. Queuing also requires that you're able to read the question and know which formula that you're going to use to answer that particular question. That's one of the things about queuing, right? You have to be able to interpret the question and match that question to the appropriate formula. Because if you use the inappropriate formula, then again, that, it's a no-go there. So we look at the formulas, right? And I want you to pay attention. Now, lambda, as I showed you before, that's Lambda, lambda, is what we use to denote the average number of arrival per period of time. So here is lambda. So here is lambda, right? So you write it like that. It's like an upside down Y. And we use that to denote the average number of arrivals per period of time. Mu, that's MU, right? This is mu. And that is used to denote the average number of people. Remember, I said people in quotation. Average number of people or items served per time. That is your average service rate. Now, after that, we use shortened forms to denote what we're talking about. So LS is used to denote the average number of units or customers or whatever cars in the system. And when we're talking about the system, we're talking about those who are waiting for service and those who are being served. And that formula is lambda over mu minus lambda. In some other places, you will see it written differently, and those formulas are okay too. You're free to adopt those other formulas if you so want to. Now, LS sometimes is just written as L or LS, right? That is the average number of units or customers in the system. WS, so W or WS, depending on where you're reading from, you may see just W. That's equivalent to WS. That's the average time, right? LS is the average number of units. WS is the average time a unit spends in the system. And again, in the system means the time that you wait in the line for your turn to get service, plus the time that you spend at the service counter getting your service. And that is 1 over mu minus lambda. Again, you may see, now I think in some places you may see lambda over mu minus lambda. That's an error, and that is to be corrected, right? So the average time a unit spends in the system is 1 over mu minus lambda, okay? while the average number of units in the system is lambda over mu minus lambda, right? So if you see this as lambda over mu minus lambda, that's incorrect. It should be 1 over mu minus lambda. Now, the following on with the other formulas, we also look at the average number of units waiting in the queue. Now notice that is LQ. That's lambda squared over mu, open bracket, mu minus lambda. Then WQ, the average number of units waiting in the queue. That's lambda over mu into mu minus lambda. So you'll find that LQ and WQ almost look alike, except for WQ has no squared in the numerator, but LQ has a square in the numerator. Now lambda over mu into mu minus lambda, that is the WQ formula, can also be found by using LQ divided by lambda, right? So WQ, you can either use lambda over mu into mu minus lambda, or you can use LQ divided by lambda. Again, you're free to adopt whichever one you want to use. Sometimes one notation is more convenient than the other. So for example, if you already knew LQ, then to find WQ is simply a matter of dividing LQ by lambda. But what if we never ask you for LQ, but we want to know WQ? Then it will be cumbersome to go and find LQ, which you never really needed, then to go find WQ. So it's good to know both of them and to be able to switch between one and the other depending on what you need to find. So again, WQ, you can either use the part of the formula I just underlined, lambda over mu into mu minus lambda, or the part that is circled and I just put a tick beside it, LQ divided by lambda, depending on the context and the question that you're asked. So you don't spend time working things you don't need when you're in an exam. You simply get straight to the point. So you're free, but you're free to adopt whichever one you wish. Just make sure it's the correct one to work the problem, okay? And then the utilization factor for the system. And this utilization factor usually tells you the probability that the system is being utilized or busy, or the probability that an arriving customer has to wait. So the utilization factor, this little animal here is called rho, R-H-O, right? The Greek letter, the elongated P is called rho. The utilization factor for the system. Sometimes you may see it being written as PW, meaning the probability that the customer will have to wait, right? So rho and PW are the same thing. They're both measuring the utilization factor from the system. One is just calling it the probability that you have to wait, and one is simply calling it the utilization factor, or we can call it the probability that the system is busy or the service provider is busy. They're all related, right? So if you look at it, consider it, you'll see that they are not dissimilar from the other. Now, we continue looking at the formulas. If we know the probability that the service provider is busy, or we know the utilization factor, or we know the probability that the customer has to wait, then we can know the corollary of that. That is the flip side. Remember that probabilities must sum to 1. So, well, going back to the utilization, if the system is not being used or not being utilized, then the assumption is that there is no one in the system, right? So if the system is not being utilized, if there's no one there in the system, we say the system is empty. There are 0 units in the system. So one of the underlying assumption is that there are only 2 states that the system can be in. It is either that it is being utilized, there's somebody there, or that the system is empty, therefore the service provider is idle. So your 2 states, you're either busy or you're idle. If you're idle, the implication is there's 0 units in the system, right? That is, the service unit is idle. Now, if the service unit is idle, it is reasonable to assume that an arriving customer will not have to wait for service. So the probability that there is 0 units in the system is equivalent to the probability that the service provider or the service unit is idle, is equivalent to, those 3 bars being equivalent to, is equivalent to that an arriving customer will not have to wait for service. Again, if you think about it, if you ponder it for a moment, you will see that they are similar things. Now, because probabilities sum to 1, if you know the utilization factor, or the probability that the service provider is busy, or the probability that the arriving customer has to wait, then you can simply subtract that, this utilization factor that you knew about from overleaf, from 1, and you will get the probability that the service system is idle. So 1 minus lambda over mu, again, 1 minus lambda over mu will tell us that the system, that the probability that the service provider is idle, or that the probability that an arriving unit will not have to wait for service, or that there is nobody in the system, P0. Now, only for 0 is 1 minus lambda over mu used, right? So 1 minus lambda over mu, imagine lambda over mu is in a bracket. So it's 1 minus, open brackets, lambda over mu, right? It is not 1 minus lambda over mu. That is wrong, okay? Instead, it is 1 minus, open brackets, lambda over mu, okay? And yes, you're 2 different things. No, the last formula is where we ask you what's the probability of more than K units in the system. So we call that the PN formula. So what if we want to know what is the probability of 3 or more units being in the system, right? Or what if we want to find the probability of 2 or more persons being in the system? If we want to find the probability of, say, 3 or more units being in the system, then it's 1. Since it is 3 or more, we don't want 0, we don't want 1, we don't want 2. So we take out what we don't want and leave what we want. So we want 3, 4, 5, 6, etc. So we find the probability of 0, find the probability of 1, find the probability of 2, and take it out of the, add them together and take it out of 1, because remember, probabilities must sum to 1. So what does the PN formula looks like? PN is lambda over mu raised to the n multiplied by P0. So n, when we're asking for n, or here k, being anything greater than 0. So if we, for the P0, remember it has its own formula, it's 1 over mu minus lambda. If we're going to find for anything above 0, it is going to be lambda over mu raised to the n multiplied by P0, where n here would be this number, n would be 1. Over here, it would be lambda over mu raised to 2, the n is 2 now, multiplied by P0, right? So only for the P0, you use 1 minus lambda over mu. For any other number, you must use the PN formula, where the PN formula is lambda over mu raised to the n multiplied by P0, right? All right, let's see if we can do a quick example. Now, in this problem, it's simple, and I know some people is going to say, yeah, we always get the simple problems in the lecture, right? No, that's true. And that's because we don't have as much time in the lecture, all right? So here you have lambda, that is the average arrival to the service station. You have 2 cars arriving each hour. And you have mu, the service rate. You have, on average, 3 cars can be serviced per hour. Note that in this problem, your average service rate and your average arrival rate are in the same unit of measurement. They are both in hours. And note also that lambda is less than mu, or mu is greater than lambda. So these 2 conditions must be met. For, remember, you can write it as lambda is less than mu. It's the same, equivalent expressions, right? So you must have your arrival and your service rate being in the same unit of measurement. whether that unit of measurement is seconds, minutes, hours, etc. If they are not in the same unit of measurement, you must make the conversion for them to be in the same unit of measurement. And the conversion can be to a unit that is not in the question. What do I mean by that? If one is in minutes, or if they're both in minutes, and one is in minutes and seconds, you can convert them to hours to make them be in the same unit of measurement, right? So, or if they are in the same unit, for example, minutes, but you notice that lambda is greater than mu, it means that you must do a conversion to get it to be in a situation where lambda is not greater than mu, or in other words, mu must be greater than lambda, right? So you must look out for that, and you must practice that in the tutorial to ensure that you get that down before you begin working a question. Because as I pointed out earlier, if you don't get that right, your results are really going to be gibberish, right? Good. So notice then again that in this question, all the assumptions are met. They are in both the same unit of time, hours, and lambda, that is the 2 cars, is less than mu, which is the 3 cars, or mu is greater than lambda. You have to learn to be able to switch between the two expressions. They are similar expressions, right? So again, our two conditions are met. Mu is greater than lambda, or lambda is less than mu, and they're both in the same unit of measurement. Remember, if they're not so, it means that you are expected to make them so by doing whatever conversion is necessary to make them so. And remember, you can convert to a unit of measure that is not mentioned in the problem. But as you rightly identify, all the conditions are met here. So we go on a little jaunt through the problem. So here we are calculating on average, and these are average numbers, right? So when we say find the average, we don't expect you to go and actually divide to find some kind of average arrival and average weight. The weights, the arrival times, and the service times are average in their description, right? So the average number of cars in the system, lambda over mu minus lambda, 2 cars in the system on average. The average waiting time in the system, 1 over mu minus lambda, is 1 hour. You notice that there are units of measurement given in the answers? Okay. And LQ gives you the average number of cars waiting in line, and yes, 1.33 cars. Remember, we're measuring the performance of the system. We don't want you to round it up or down because we want to see exactly what is going on in the system. Right? So you keep the decimal places up to 2 decimal places. The number of, or the time spent waiting, WQ, it's 2/3 of an hour or 40 minutes. So notice we didn't just write 2/3 or 40. Units of time are attached, or units of measurement are attached. So I don't want anybody just giving me 2/3 or 40, 2/3 watt or 40 watt. Your units of measurement must be there. And our rho, or the utilization of the business. Now remember I said that rho is sometimes written as PW. So these are equivalent. PW is equivalent to rho, and that is lambda upon mu, and that is your utilization rate, or the time the service provider is busy, right? And P0, it is the probability that there's 0 cars in the system, or probability that the service provider is idle, or the probability that an arriving customer doesn't have to wait for service. Good. And so the things to look out for, or the things to look out for when you are doing a queuing problem, one is to be able to properly identify your lambda, your mu, to assure yourselves that lambda is less than mu, or mu is greater than lambda, and that they are in the same unit of time. And remember, if 2 and 3 are not met in the problem, then you must make them meet. Or if 1 is met and the other is not met after having identified what lambda and mu is or are, then you must make sure that that is rectified before you begin the problem. After that is just to be able to interpret the questions and match the questions to the appropriate formula. And so if you're able to do that with practice, you're good to do a queuing problem. But of course, it takes a little bit of practice, or it may take more practice for some of us. But either way, practice is required, and practice is a part of learning. So it is okay if looking at it once you still have questions. Look at it a second and a third time, and you come to the tutorials with whatever questions you have, and we will sort them out there. So a little bit of economic analysis. Here's a problem that says customer dissatisfaction and lost goodwill will be $15 per hour, right? Your waiting time, you wait, it is 2/3 of an hour. So WQ, that is waiting for service, is 2/3 of an hour. Total arrivals for the day, 16 persons for the day. The mechanic's salary is $88 per day. So what would an economic analysis of the queue looks like? Well, you look at the total hours customers spend waiting per day. If 16 customers arrive for the day, if 16 customers arrive for the day, so 16 customers arrive for the day, and each spends 2/3 of an hour waiting for the day, then the total time the customer spent waiting for the business day is 10 and 2/3 hours. Now remember that customers don't like to wait, right? So we're assuming that the customers are dissatisfied and the company loses goodwill when the customer has to wait. And that is $15 per hour in terms of lost goodwill. And so if the customers waited in total 10 and 2/3 of an hour, that is the 16 customers waited in 10 and 2/3 of an hour, then the customer's wait time cost is $160 per day. So the queue costs you not only the $88 that you pay the mechanic to work per day, it is costing you this $160 from customer dissatisfaction and loss of goodwill. So the total expected cost of that queue is $248 per day, not just the $88 that you're seeing coming out of your pocket. There is this, call it unseen cost of $160, way more than the mechanic salary. So that is how we can use a queue characteristic to help us to assess what is going on with the queue. So you may think you're being, cheap in just paying the mechanic $88, and you're employing one mechanic, but it's not just the seen cost of the mechanic's salary that you're losing or you're incurring in terms of cost. There is goodwill and customer dissatisfaction that is causing you to lose money also. Yes, we know that goodwill, the accounting students will say, but goodwill is difficult to cost. Yeah, we know that. But you can still use mechanism to cost goodwill, which you do in accounts all the time, right? So that is what economic analysis can look like. There are multiple other economic analysis that can be done, but this is one such way that we can use the characteristic of the queue to assess what is going on in the queue. So simple economic analysis like this, we expect that you will be able to wrap your head around and to conduct, okay? And so that takes us to the end of our lecture. Now, just to point out that we have different queues where we have multiple server, but just to let you know that we don't normally teach you multiple servers here, because just to give you an idea of the mathematics, that the more complicated the models, the more complicated the mathematics of the model. So if you look at the P0 for a multiple server system, you will see that whereas in the single server, P0 was just simply 1 minus lambda over mu. Look at what it looks like for a multiple server. So P0 in the single server was 1 minus lambda over mu. Look at all of this that P0 has become for a multiple server. So we stick to just the simple single server, single queue, and because it becomes much more difficult here, and not that you cannot learn it, but the time and the level doesn't require these complexities at this point, right? So we usually end where we ended previously, right? So then we go back to the end. Questions or comments? If you have questions and or comments, then tutorials is where we deal with those. Okay, and I expect you to come with your questions or comments to the tutorial. All right, it was good talking to you. We will see each other in the tutorial. Righty? Have a good evening.